Welcome student in Christchurch Convent Digital Classes, subject Chemistry, class 11th, chapter 4, hybridization of element involving d orbitals. So in this video we'll study about the orbitals which are involved in the hybridization are s, p and d also. So the energy of the 3d orbital are comparable or almost nearly equal to the energy of the 3s and 3p orbitals. The energy of 3d orbital are also comparable to those of 4s and 4p orbitals. So as a consequence of the hybridization involving either 3s, 3p and 3d or 3d, 4s and 4p is possible. So since the difference in the energies of 3p and 4s orbital is significant, no hybridization involving 3p, 3d and 4s orbital is possible. So the important hybridization scheme involving s, p and d orbital are summarized below. So as you can see in the formation of PCl5 phosphorus pentachloride, sp3d hybridization is involved. So dsp2, if there is a dsp2 hybridization, then 1d, sp and 2p orbitals are involved. So summarized below in the table, dsp2, sp3d, sp3d2 and sp3d2 or d2sp3, and examples are also given. Now first of all we will see the formation of PCl5 or sp3d hybridization in the ground state and the excited state of outer electronic configuration of phosphorus whose atomic number Z बराबर 15 are represented below. P in ground state 3p 3s में 2 रहेंगे, 3p में 1 रहेगा, 3d पूरा खाली रहता है. लेकिन फास्फोरस की एक्साइटेड स्टेट में 3s से एक इलेक्ट्रॉन निकल के 3d में चला जाता है. इस प्रकार क्लोरीन के 5 एटम 3s, 3p और 3d के अनपेयर्ड इलेक्ट्रॉन से पेयरिंग करके PCl5 बना लेता है. So sp3d hybrid orbital filled by electron pairs donated by 5 chlorine atoms. And its trigonal bipyramidal geometry of the PCl5 molecule is trigonal bipyramidal, as you can see in the figure 4.17. Formation of SF6 sulfur hexafluoride. In this sp3d2 hybridization take place. As you know, you can see the ground state electronic configuration of sulfur is 3s में 2, 3p में 4, 3d पूरा खाली है. एक्साइटेड स्टेट में 3s और 3p के जो पेयर्ड इलेक्ट्रॉन है वो भी अनपेयर्ड हो जाते हैं और 3d में 2 इलेक्ट्रॉन प्रकट हो जाते हैं या प्रेजेंट हो जाते हैं, हायर एनर्जी लेवल में चले जाते हैं. फिर हाइब्रिडाइजेशन के कारण 6f फ्लोरीन एटम सल्फर के 6 अनपेयर्ड इलेक्ट्रॉन से पेयरिंग करके SF6 बनाते हैं. तो इस टाइप के हाइब्रिडाइजेशन में sp3d2 हाइब्रिडाइजेशन होता है. तो जस्ट रिमेंबर द टाइप ऑफ हाइब्रिडाइजेशन इज एग्जांपल एंड जस्ट शो इट बाय इलेक्ट्रॉनिक कॉन्फ़िगरेशन. एंड ऑक्टाहेड्रल ज्योमेट्री, SF6 मॉलिक्यूल की ज्योमेट्री जो है वो ऑक्टाहेड्रल होती है. कॉम्प्लेक्स सॉल्ट की ज्योमेट्री अभी कोर्स के बाहर है अभी आपके. Now next important theory is molecular orbital theory, MOT, in short MO theory. So molecular orbital or MO theory was developed by F. Fund and R.S. Mulliken in 1932. The silent feature of this theory are First, the electron in a molecule are present in the various molecular orbital as the electron of atoms are present in the various atomic orbitals. The atomic orbitals of comparable energies and proper symmetry combine to form molecular orbital. Second point. The third point is, while an electron in an atomic orbital is influenced by one nucleus, in a molecular orbital it is influenced by two or more nucleus depending upon the number of atoms in the molecule. Thus, an atomic orbital is monocentric while a molecular orbital is polycentric. Fourth point. Fourth point. The number of molecular orbital formed is equal to the number of combining atomic orbitals. When the two atomic orbitals combine, the two molecular orbitals are formed. One is known as bonding molecular orbital, which has a lower energy, and the other is called anti-bonding molecular orbital, which has a higher energy. It is mentioned in fifth point. Bonding molecular orbital has lower energy, hence greater stability than corresponding antibody molecular orbital. Just as the electron probability distribution around a nucleus in an atom is given by an atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by a molecular orbital. Seventh point. The molecular orbital, like atomic orbital, are filled in accordance with the above principle, obeying the Pauli's exclusion principle and Hund rule also. The formation of molecular orbital or linear combination of atomic orbital, in short it is called LACO, LACO, linear combination of atomic orbital, LACAO. According to wave mechanics, the atomic orbital can be expressed by the wave function psi, which is represented by the amplitude of the electron waves. These are obtained from the solution of Schrodinger wave equation. However, since it cannot be solved for any system containing more than one electron, molecular orbital which are one electron wave function for molecules are difficult to obtain directly from the solution of Schrodinger wave function or equation. To overcome this problem, an approximate method is known as linear combination of atomic orbital has been adopted. Let us apply this method to the homonuclear diatomic hydrogen molecule. Consider the hydrogen molecule consisting of two atoms A and B. Each hydrogen atom is in the ground state and has one electron in one s orbital. The atomic orbital of these atoms may be represented by the wave functions psi A and psi B. So, mathematically, the formation of molecular orbital may be as described as by the linear combination of atomic orbital that can take place by addition and the subtraction of wave function of individual atomic orbital as shown below. Psi mo means psi molecular orbital is equal to psi a plus minus psi b. त्रिशूल जैसा साइन psi कहलाता है. Therefore, the two molecular orbitals sigma and sigma star are formed. So sigma will be equal to psi a plus psi b and sigma star is equal to psi a minus psi b. So the molecular orbital sigma formed by the addition of atomic orbital is called bonding molecular orbital, while the molecular orbital sigma star formed by the subtraction of the atomic orbital is called anti-bonding molecular orbital. So as you can see in figure 4.19, on the right hand side with yellow color, figure 4.19, the formation of bonding sigma and anti-bonding sigma star molecular orbitals by the linear combination of atomic orbitals psi a and psi b centered on two atoms A and B respectively. So you can see there are one electron in psi A and one electron in psi B. So and there are 2 electrons in sigma, which is equal to psi a plus psi b, and in sigma star psi a minus psi b there is no electron, shown with pink color. So sigma, which is equal to psi a plus psi b, as shown in the figure 4.19, bonding orbital having lower energy than the atomic orbitals, and in sigma star in the figure 4.19 have empty, it has no electron, and sigma star is equal to psi a minus sin b, which is called anti-bonding orbital, higher energy than that of atomic orbitals. So this is the formation of, in figure 4.19, formation of bonding sigma and anti-bonding sigma star molecular orbital by the linear combination of atomic orbitals I and sin b centered on two atoms A and B respectively. Qualitatively, the formation of molecular orbital can be understood in terms of the constructive or destructive interference of the electron waves of combining atoms. In the formation of bonding molecular orbital, the two electron waves of the bonding atoms reinforce each other due to constructive inference, while in the formation of anti-bonding molecular orbital, see on the left hand side, the electron waves cancel each other due to destructive interference. As a result, the electron density in a bonding molecular orbital is located between the nuclei of the bonded atoms, and because of which repulsion between the nuclei is very less, while in case of an anti-bonding molecular orbital, most of the electron density is located away from the space between the nuclei. In fact, there is no nodal plane on which the electron density is zero. So thank you for watching. See you in the next video. We'll see in the next video the condition for the combination of atomic orbital and types of molecular orbitals. We have time in this video, so we'll continue 5 minutes more. The conditions for the combination of atomic orbital is: first, the combining atomic orbital must have the same or nearly the same energy. Second, the combining atomic orbitals must have some symmetry about the molecular axis. Third one, the combining atomic orbitals must overlap to the maximum extent. Now we'll see types of molecular orbitals. Molecular orbitals of diatomic molecules are designated as sigma, pi, and delta etc. In this nomenclature, the sigma molecular orbital are symmetrical around the bond axis, while the pi molecular orbital are not symmetrical. For example, the linear combination of 1s orbital centered on two nuclei produces two molecular orbitals which are symmetrical around the bond axis. Such molecular orbitals are of the sigma type and are designated as sigma 1s and sigma star 1s. Its internuclear axis is taken to be in the z direction. It can be seen that a linear combination of two pz orbitals of two atoms also produces two sigma molecular orbital designated as sigma 2pz and sigma star 2pz. Molecular orbitals obtained from 2px and 2py orbitals are not symmetrical around the bond axis because of the presence of positive lobes above and the negative lobes below the molecular plane. Such molecular orbitals are labeled as pi and pi star. A pi bonding molecular orbital has larger electron density above and below the internuclear axis. The pi star antibonding molecular orbital has a node between the nuclei. So we'll see what are this one by one. Energy level diagram for molecular orbital we'll see in this. So in the next video we'll see hydrogen bonding. Thank you for watching. See you in the next video.